Welcome to the series of lecture on solar energy fundamental. In this lecture, we will discuss the local centric coordinate system to define the zenith angle, azimuth angle and other important angle including the angle of incidence. Now the question might be hovering in your mind why we need to know the local centric coordinate system and its associated angles. Can't we work without the subject without knowing the complex solar geometry? Answer of your query is all the solar devices, either it is a solar panel or solar flat plate collectors, solar concentrator or any other solar devices which are installed on the earth surface, instead of they are installed on the equatorial plane. Since earth is spherical in shape, then the devices which are lying on the earth surface can never be parallel to the equatorial plane, and hence the sun radiations which received by the surface will be at different angular position than the object if placed parallel to the equatorial plane. So, for precise evaluation of performance of the solar devices, the knowledge of these angles is primary requirement. In previous lecture, we have learned about the earth-centric coordinate system. The same figure is reproduced for the sake of understanding. As we saw earlier, here are polar axis, meridional axis and equatorial axis. All these three axes emerge from the center of the earth and extended to their respective direction and the perpendicular to each other. Now let us assume a point P on the earth surface and assign some coordinates to this point to define its location. Say its coordinates are 28.5 degree north and 77.5 degree east. Say its coordinates are 28.5 degree north and 77.5 degree east. These coordinates indicate that this point somewhere on the earth surface is lying in Delhi, India. Now join this point with the center of earth, and this line constitutes an angle phi with the equatorial axis is an angle of latitude. Since point is located at the latitude of 28.5 degree north, so the angle phi is also of the same magnitude, that is of 28.5 degree. I hope you all understand this fact because we have already learned about this in previous lectures. This point, this yellow point is the point of our interest, and origin of the local centric coordinate system lies on this point. Now let us place a negligible thickness rectangular plane at this point. As you can see, this plane is not parallel to the equatorial plane because of the obvious reason that the earth has spherical shape. However, for an observer standing at this point on earth's surface, it appears for the observer that this plane is horizontal to the ground. Since it appears to be horizontal to the observer, this plane or this rectangular object is called horizon plane as a reference. Now the line which is emerging from the center of the earth and intersecting the point, yellow point on the earth surface, be further extended. This line is normal to this horizon plane and named as the zenith axis or z axis we can say. The other axis emerges from the origin on the local point, the other axis emerging from the origin on local point on the horizon plane. The other axis emerging from the origin on local point on the horizon plane along the meridional axis and orthogonal to the zenith axis and going down to the south. This line is tangential to the meridian 77.5 degree east on which this line will be denoted by S, which represents the south direction. The third coordinate axis, which is orthogonal to both zenith and south axis, is extended to east, so it is named as east axis. This east axis of the local coordinate system is parallel to the equatorial axis of the earth centric coordinate system and extended in the same direction. So all these three axes comprising the zenith axis or z axis, south axis or s axis, east axis or e axis form the local centric coordinate system. Now let us draw three axes that are perpendicular to one another. The axis that faces you is the meridional axis. It is a replica of the equatorial coordinate system. Now let us mark a point P on this meridional plane that corresponds to the surface of the earth. If we connect point P to the earth center O, the angle formed by this line and the meridional axis is called the latitude angle. We are already aware of it. Now if we draw a line passing through this point P, this is tangential to the meridian of the place at point P and it is perpendicular to OP. So this angle P is actually the 90 degree angle. This line intersects the meridional axis at point B. This triangle POB is a right angle triangle because angle P is 90 degree and angle PBO is nothing but it is equal to the angle BPO minus angle POB, and here angle BPO is 90 degree and angle POB is the angle of latitude of the place. We can draw from here that any rectangular object which is laying horizontally on the earth's surface at point P is inclined to the equatorial plane, and the angle of inclination of that object can be obtained simply by subtracting the angle of latitude of the place from the right angle, that is 90 degree. Similar to this, you may determine the inclination of the horizontal surface with the equatorial plane at any point on the earth's surface. For reference, the points Q, R, S are shown on the same meridian, and for these points the inclination can be obtained in the similar way by subtracting the angle of latitude of the point either Q, R or S from 90 degree. Let us draw local centric coordinate system on a plain paper, assuming that this blue rectangular surface is a horizon plane which is laying on the earth's surface and having an inclination equal to 90 degree minus the latitude of the place where this horizontal surface is lying on the earth's surface with respect to equatorial plane. But here it appears to be horizontal and axis normal to the surface is zenith axis. So this zenith axis is normal to the surface. Assuming that this plane is located in northern hemisphere, then to receive maximum sun radiation it will be facing south. The axis toward the south is termed as S axis, and the third one which is extended to east is E axis. Now suppose the sun radiation, I mean the insolation, which this term we are regularly using, is striking to the point P on the horizon plane, or we can say the earth's surface. The angle between the zenith axis and insolation is called as zenith angle. This angle is of importance to the designer and installer because it helps in estimating the length of shadow of nearby building, trees, etc., so that solar devices can be installed to avoid shadowing. Also, this angle helps to estimate the amount of radiation received on the horizontal surface on any day of the year. The angle between the insolation and its shadow on the earth's surface or horizon plane is called the angle of latitude, represented by alpha A. This angle is complement to the zenith angle. So this theta z is the zenith angle and alpha A is the latitude angle, and these angle having a relation because both are complement to each other. Theta z plus alpha A is equal to 90 degree, or we can say the alpha A is equal to 90 degree minus theta z. This angle of latitude tells the height of the sun in the sky at any time of the day or year. Another angle is the angle between S axis and the line PA, which is the projection of the insolation on the earth's surface, is called the azimuth angle. This angle gives the direction of the shadow. Here again we choose the horizon plane, but shape this time is oval instead of the rectangular. The shape of the horizon plane makes no difference. That is why this shape is chosen just to give the another view to you. It shows all four directions, that is north, west, due south and east, and the direction which faces you is the due south. Further, like horizontal plane, it has axis which is normal to the plane, and the insolation which strike to the horizon of the zenith axis also it shows the projection of the sun insolation, and showing all the three angles, that is zenith angle, altitude angle and azimuth angle. So it is clear from it that the shape of the horizon plane has nothing to do with the formation of angle. Instead, it is the axis and insolation plays the part. For more insight, if we view this oval shaped plane from the front, and we'll develop a 2D front view of it. Here one can visualize this arrangement from the front. Then the horizontal plane represents the horizon plane, and vertical line which is normal to it is zenith axis. Sun appears to rise from east and its radiation strike to the foot of the zenith axis. Then the angle so constituted between the insolation and zenith axis is the zenith angle, and complement to it is between the insolation and its projection is the altitude angle. Till now we saw that the surface is horizontal and it is receiving the radiation and at an angle of theta z, that is the angle of incident on the horizontal surface as shown in the figure. The insolation coming from the sun are called the beam flux and represented by IB, and considering these radiations falling on the earth's surface and are normal to the surface, then their intensity is represented by IBN. But the radiation received by the horizontal surface will be IBN cos theta z, because the insolation or these beam flux are inclined at an theta z to the surface normal. As the equation shows, lesser the value of theta, more will be the intensity of the falling beam flux on the surface, on the horizontal surface. So if theta z is equal to 0, in that case cos theta z will be value 1 and IBN will be equal to the IBN cos theta z. But this situation arises only at a place on the earth's surface when angle of declination is equal to the angle of latitude of that place, and also at the solar noon. And this situation can happens once in a year between the Tropic of Cancer and Tropic of Capricorn. As we saw, this is the horizontal surface. We are just reproducing it, and this is the point P, and this is the normal to this surface. Therefore, the installer always try to reduce the value of theta z so that the beam flux which are received from the sun should be normal to the surface, or we can say the as normal as possible. And that's why the surfaces are tilted at certain angle as shown in the figure, and the tilt is designated by angle beta. So when surface is tilted, then the normal to the horizontal plane will no more normal to the tilted surface. The normal to the surface will be different as shown by a red line. Now the sun radiations which are falling at point P, and it constitutes angles with the red line and the black line. So the angle constituted with the red line, which is normal to the inclined surface, is known as the angle of incidence, and if it constitute an angle with normal to the horizontal surface, this is called the theta z. So by tilting the angle by beta, we have seen that the value of, so by tilting the surface, the insolations or the solar radiations which are falling on the surface are near to normal, and hence the value of the intensity of the radiation on the surface is increasing. Also, it is shown that the solar azimuth angle is the angle between the line due south and the projection of the solar radiation on the inclined surface. The projection of the normal to the inclined surface and the line due south, they constitute an angle, and that angle is known as the surface azimuth angle. Till now we have seen that the zenith angle, angle of incidence, solar azimuth angle and surface azimuth angle, these angles are very much of importance to the installer or the people who are working in the field of installing the solar devices at various locations. Zenith angle, which is represented by theta z, is used to estimate the length of the shadow. It means wherever we are installing solar devices, so nearby if there is any kind of obstruction like a building, trees or any other kind of tower is there, its shadow should not fall on the device. That can be estimated with the help of the zenith angle. Where the solar azimuth angle gamma, it is used to measure the direction of the shadow. Since the sun is rising from east and set at west, and also it follows certain path in the sky, because of that the direction of the shadow and its length both are changing. So that's why this zenith angle and solar azimuth angles are of much importance for the installer. Another angle is the surface azimuth angle. This angle helps to fix the direction of the surface with respect to the sun. Suppose if we need to install the devices in the northern hemisphere, so in the northern hemisphere the sun is always in the south direction, so that's why the surfaces should have the direction towards the south. So either they are little bit of southeast or southwest, then what will be its impact on that can be estimated with the help of the surface azimuth angle. And another important angle is the angle of incidence. It is used to estimate the amount of sun radiation received by the inclined surfaces. This is what a kind of input we are giving to the solar devices, and on the basis of the input we can calculate the performance by knowing the output from the installed devices. The angle of incidence theta is the angle between the incident solar beam fluxes, and this angle is a function of latitude, declination, tilt angle, azimuth angle and the R angle. Cos theta is a function of phi, delta, beta, gamma and omega. So based on the above relation, the angle of incidence is expressed here in the form of this equation. Cos theta is equal to sin phi within bracket sin delta cos beta plus cos delta cos gamma cos omega sin beta bracket close plus cos phi within bracket cos delta cos beta cos gamma minus sin delta cos gamma sin beta plus cos delta sin gamma sin omega sin beta. It means by knowing the latitude, sun declination, tilt of the surface azimuth angle and R angle, the beam flux which are incident of the surfaces can be calculated. In the coming slide, the special cases are taken, and for these cases the general equation of angle of incidence has been reduced as per the given condition. These special cases are vertical surfaces which facing the due south, then horizontal surface which facing due south, and inclined surface facing due north. Now we are going to discuss the special cases where the surfaces, they might be vertical or horizontal, they are facing due south, or they are making certain angle with the horizontal surface. So this is the first case. We are taking the surfaces vertical. In case of vertical, the tilt angle beta should be equal to 90 degree. We have already seen that equation of cos theta means the angle of incidence is having certain relation with the different angles of latitude, declination, tilt angle, surface azimuth angle and R angle. So this equation is reproduced here, and normally we know that the surfaces which we come across, these surfaces having certain inclination with the ground beta. So but in this case what we are taking, that beta is 90 degree, it means the surfaces are installed like this, means there is no angle between them. So in that case, if you'll see, if you place the value of beta in the equation, so here is the cos beta at two places. If you place the value of beta here, then this term becomes 0, and in case these terms of sin beta are here, if you place the value, they will become 1, and the new equation will be like this. So in this equation it is clear that sin delta into 0, because cos 90 is 0, and similarly the cos delta into 0 into cos omega, because here again the cos beta is 0, and in this case since sin beta is 1, so this equation will be like this, and the new equation will reproduce. By substituting the value of beta in the equation, we will get the new equation of cos theta, means angle of incidence. If the surface is vertical, then we can write this equation. Another case is if the vertical surface is facing due south, so in that case, of course, the one term is beta is equal to 90 degree. Along with that, the surface azimuth angle is also 0 degree, because the surface is facing due south. And the generalized equation of the angle of incidence is reproduced here, and it has been shown here that cos gamma, sin beta, these are the two angles, the beta and gamma are reflected here. So this cos beta, cos gamma, cos sin beta, if we place the value of these terms here, so we are knowing that we place the value of sin 0 is 0 and sin 90 is 1, and cos 0 is 1 and cos 90 is 0. So if you place these values here, the equation will be cos gamma and sin beta will be 1, and by placing the value of cos gamma here, this cos gamma, sin beta, cos gamma and sin beta in this equation, the new equation will be like this, and the value of cos beta and sin gamma will be 0, and the new equation will be here. In that case, all the terms of cos beta and sin gamma are replaced with 0, and cos gamma sin betas are replaced with 1. Further, the equation is reduced by substituting the value of the respective angles, and here this term, the sin delta into 0, and this cos phi into 0, and this term is already 0 here, which is already written here, this is 0. So by substituting this value and multiplying the terms, the final equation comes out to be this is the cos theta is sin phi cos delta cos gamma minus cos phi sin delta. It means the angle of incidence in this particular case, when the surface is facing due south, having no effect of the surface azimuth angle, because already it is facing south, and since the surface is vertical, so the term beta is also been excluded from here, and the final equation for this kind of cases will be simply we can write like this. Next special case is horizontal surface. We are already aware that in case of the horizontal, the angle of tilt is 0, means any of the solar device, either it is a solar panel, solar water heater, or any other kind of solar device, they are lying simply on the ground, just like this. And equation we are already well versed of. This is a generalized equation, and here the highlighted the sin beta, and by placing the value of beta is equal to 0 here, we'll get a new equation, that is cos theta is sin phi sin delta cos beta cos phi cos delta cos beta cos gamma. And if similarly in the above equation the value of beta, means we'll place here in the cos beta, these are the terms where we can place the value of beta, and cos 0 is 1, we are already knowing it, and by placing this, the final equation will comes out to be, it will reduce to a few terms, simple equation that you can write here. Cos theta is equal to sin phi sin delta cos phi cos delta cos omega. Since the surface is horizontal, and if you recall the definition of the angle of incidence or the zenith angle, if the surface is horizontal, then in that case the normal to the surface in this case is the line which is coming out from the center of the earth and passing through the point on the earth surface, and hence in that case the angle of incidence is equivalent to the zenith angle. So here we can replace this term cos theta with cos theta z also, both are one and same thing. Next one is the inclined surface which is facing due south. So certain inclination is there, beta having certain value which is lying somehow between 0 to 90 degree, but it is facing due south. So for that surface again the equation is reproduced here. Terms of the cosines and sines are highlighted where they are containing the angle gamma. So if you substitute the value of gamma here, then the new equation will comes out to be cos theta is equal to sin phi within bracket sin delta cos beta plus cos delta cos gamma sin beta, because here the cos gamma will be cos 0 is 1, and the next term will be cos phi cos delta cos beta cos gamma, and here again the cos gamma is 1, so this term will be sin delta sin beta. But this term, since sin gamma is 0, so this term becomes 0, and we are not going to reproduce here. Further this term can be expanded and reproduce here, cos theta is equal to this, and by further simplification finally we can have this equation, that if the surface is inclined and facing due south, so then in that case the cos theta will be nothing but it's a sin delta sin phi minus beta plus cos delta cos gamma cos phi minus beta. Another case is surface is inclined but it is facing due north, means just opposite, you have turned the face 180 degree to the surface, whether you are in the northern hemisphere or the southern hemisphere. So in that case this equation will reduce to this, cos theta will be sin delta sin phi plus beta sin phi plus beta plus cos delta cos gamma plus cos phi plus beta. So these two terms, cos theta for the surface facing due south, having only the difference is phi minus beta, and the surface which is facing due south having a phi plus beta. Rest of the equation is same. Angle of incidence, that is theta, can be expressed in terms of the zenith angle. So we have already been seen that if the surface is horizontal, so in that case the angle of incidence is zenith angle, but for the audience it is again reproduced. We know that the cos theta, whole of the equation of the generalized equation which having a impact of so many angles is reduced to a small numbers of terms, and the equation has been shortened by considering that theta z, beta and gamma minus gamma s, that is the solar azimuth angle and surface azimuth angle. Cos theta z already been developed. This is if the surface is lying horizontal, and this is the special case of solar azimuth angle. The cos gamma can be calculated by using this angle. So students can solve many numerical problems by remembering these equations directly. They'll save their time.